to give welcome address.
Good morning to everyone, and welcome you all for today's webinar on advanced carbon material for storage. I feel privileged to be here and welcoming everyone. Respected Principal Madam, today's resource person Dr. Karthik, my dear colleagues, teaching faculties, researchers, and students from various institutions, warm greetings to one and all. On behalf of Chemistry Department of Chikana Government Arts College, I extend a pleasant welcome to our beloved Principal Madam Dr. C.V. Deepa. She joined in our institution as Principal a year before. During this period, she has taken a lot of efforts and new initiatives for the betterment of knowledge. Madam is a chemistry professor. We are fortunate to have a principal from our own chemistry background. Welcome, Madam. Next, I extend my warm welcome to our speaker, Dr. Karthik, a senior scientist from International Advanced Research Center for Powder Metallurgy and New Materials, Hyderabad, an autonomous body under Department of Science and Technology, Government of India. It's giving me a great pleasure to welcome an excellent scientist and researcher for this webinar. The topic we have chosen for today's lecture is advanced carbon materials for energy storage. For current scenario, the topic is very important. Energy resources are not only parts but also means of our future industrial growth and developments that have societal impact. Seeing current energy crisis, scientific community has started focusing their research activities on energy-related novel materials. The International Energy Association, IEA, estimates that in order to keep global warming below 2 degrees Celsius, the world needs 266 gigawatts of energy storage by 2030. Lithium-ion batteries, which power portable electronics, electric vehicles, and stationary storage, have been recognized with the 2019 Nobel Prize in Chemistry. Being small, doing big. That's our nanomaterial. The development of nanomaterials and their related processing into electrodes devices can improve the performance and development of the existing energy storage system. Thinking small to store more, from mobile devices to the power grid, the needs for the high energy density or high power density energy storage materials continue to grow. I hope today's topic is relevant and needed for the current energy storage crisis. Thank you very much for choosing this topic, sir. On behalf of organizing committee, I welcome Dr. Karthik, scientist for this August function. Welcome, sir. Next, I would like to welcome the organizers for the webinar, Dr. S. Karthik and Dr. N. Sivakumar. They are the key instruments for this arrangement. Welcome, professors. Particularly, Dr. S. Karthik is one of the notable person in the area of carbon nanomaterial research, and Dr. N. Sivakumar for absorption studies using new materials. My special welcome to Dr. N. Sambat Kumar, IQAC Department Coordinator, who has initiated and scheduled all these activities. Welcome, Dr. Sambat Kumar. It's my duty to welcome all my department colleagues who are always supporting and doing teamwork for any kind of academic activities, both at the department level and college level. Welcome, professors. Without this person, no one can enter in this webinar room. Is our moderator, Dr. P. Vijayan, who is technically coordinating all our virtual activities. A special welcome to Dr. Vijayan. With the glimpse of this, I welcome the participants from various institutions, senior professors, faculties, researchers, and students. Welcome you all. Thank you. Now I call upon Dr. S. Karthik to introduce the speaker. Dr. Karthik.
Yes, sir. Very good morning to all. Our respected chief guest, Dr. Karthik, our beloved principal, respected head of the Department of Chemistry, Dr. G. Rajagopal, Dr. Raja Singh, Dr. N. Sivakumar, Dr. Shivadayanidhi, Dr. Shampath, Dr. Vijayan, Dr. Kaniappan, Dr. Sujata, Dr. Satya, Dr. Balamani, cherished faculty members, most valued delegates, my dear friends, very good morning. It gives me a pleasure to introduce our chief guest, today's speaker of our third webinar of our webinar series for the year 2020, organized by the Department of Chemistry, Chikana Government Arts College. We are honored this morning by the presence of our special speaker, Dr. Karthik, senior scientist, ARCI, Hyderabad, Telangana, India, and he is giving present guest lecture on the topic Advanced Carbon Nanomaterial for Energy Storage with a special reference to supercapacitors. He is a real source of energy and inspiration for all today. Dr. Karthik is currently working as a senior scientist in the Department of Center for Nanomaterials in International Advanced Research Center for Powder Metallurgy and New Materials, held in Hyderabad, Telangana, India. Dr. Karthik has also worked at a different organization located in South Korea, Taiwan, Italy, and Spain. He has received several research fellowships from the University of Torino, Italy, National Science Council, NSC, Taiwan, Korea Advanced Institute of Science and Technology, South Korea, UGC, and the Department of Atomic Energy, India. Indian Embassy in South Korea has selected him as one of the best Indian scientists for the scientific interaction with our late Honorable Dr. APJ Abdul Kalam, former President of India, during his president visit at Seoul, South Korea in the year 2006. Dr. Karthik has received an award, the Best Scientist in Supercapacitor in the year 2019, awarded by Rula Award, powered by World Research Council and United Medical Council. His research area of specialization include material science and nanotechnology, porous carbon materials, catalysis, fine chemical synthesis, air quality management and pollution control, solar energy harvesting, energy conservation and storage, batteries, and supercapacitors. His research papers are frequently cited and also appeared in the cover pages of many reputed journals. He has served as a guest editor for Material Focus. This is a prestigious journal of American scientific publishers. Till date, Dr. Karthik filed 9 patents. Out of these, 7 has been published and 2 has been granted. He published more than 60 research articles in research reputed journals and published 3 books in online book chapter. He has been presented research papers and chaired in more than 35 international conferences all over the world. Dr. Karthik is acted as an editorial board member in more than 5 reputed journals. He is such an eminent personality. On behalf of our department and my own behalf, my sincere thanks to Dr. Karthik. Beside his tight schedule, he accepted to give the special lecture today. We are really honored by your presence on this occasion, sir. Thank you, one and all. Now, I hand over the forum to Dr. Karthik. I request all delegates to maintain the decorum. After completing his Dr. Karthik's speech, the question session will start. After that only, the feedback form will give to all delegates. Please, I request all delegates to maintain the decorum. Thank you very much. Sir, the forum hand over to Karthik. Karthik, sir, please take it.
Yeah. Thank you. Can you hear me now?
Yeah.
I'm audible?
Yes, sir.
Yes, sir, you are audible, sir, and you can share your PowerPoint.
Yes. Mike. So actually, I am from the International Advanced Research Center for Powder Metallurgy and New Materials. It is located in Hyderabad. You can see this is our center. So actually our main activities of this ARCI is technology development, technology demonstration, and technology transfer. Actually, I am coming from the nanomaterials. The nanomaterials focus on nanostructure materials and carbon materials and nanocomposite coating. And also we are focusing on energy, alternative energy, surface engineering, ceramics, laser processing, and alternative materials for the energy sectors. So I am audible, right? Hello?
Sir, yes, sir, you are audible, sir.
Okay, fine. So actually, as I said, the technology transfer forum, ARCI has developed a different type of materials for the technology transfer to the Indian industry. Here you can see the nanomaterials for antibacterial and self-cleaning textiles is the coating of nano silver and TiO2 microsphere. Actually, we have developed the technology and transferred to the Resil. There's Indian company is the manufacturers of the cloths, jeans, and other socks and all. They are coated in nano silver for antibacterial and self-cleaning textiles. So for this, actually, our is the best award we got received from the President of India, ex-President of India. We are developing the silica aerosols, flexible foams of thermal insulations, other prototype materials. You can see that in the slides. So this is Center for Nanomaterials. This is our research group. So actually, in this today, the topic is energy sectors. So in the consider energy sectors, you see the mechanical energy and the chemical energy, electrochemical and the electric energy. There is different sectors. Mechanical energy, see the underwater compressor or wind power, everyone knows. The chemical energy is a hydrogen sectors. Hydrogen is one of the fuels. Is it can be used for our hydrogen vehicles in future. But both technologies little bit undeveloped and also it is come to the market because of some expensive and as well as safety issues. Now electrochemical energy storage, for example, batteries, fuel cells, solar cells for electric, for particularly capacitors and capacitor modules. We are going to focus on this topic today. Then why we need energy storage? For example, there is a power generation from the thermal power plant as well as these PV sectors, photovoltaic. But there is another sector. If you can see the transmission and the distribution of our power grid and also the power to the society. So because of there is another sector is the consumption is there for the consumers, for the society, for different applications. So why we need energy storage? Because power generation, sometimes the power generation is having the surplus energy generation that also we need to store. Sometimes it's a demand. So power demand, for example, if you see any power shutdown or something, so we get the energy storage that is useful for the application. So in this case, lithium-ion batteries, redox flow batteries, sodium-ion, and supercapacitor as a energy storage. So whenever the power demand, then we need to have some backup for the energy storage. And the other sectors, whenever we have a surplus of the energy generation, that also we need to store in the devices. So that's the reason we need to focus on the energy storage devices. But every energy storage device is having some unique features because it depends on the energy density of the material, how they are stored, and the volumetric energy density, gravimetric energy density depends on there, and depends on the need that people are choosing the technology. So electrical energy storage in the concern, lithium-ion batteries and supercapacitor, the two sectors is there. We are focusing on lithium-ion batteries as well as supercapacitor. You can see the lithium-ion battery supercapacitor. Actually, there is a lot of different sectors are there: elevation, mobility, and the stationary applications. Elevation, you can see the elevators or the grinds and all. You can see this mobility and all. For example, the transportations for car and trains and whatever this is. Stationary application is grid applications and, for example, for the windmill. So these are the mainly I am talking. There is a lot of energy storage devices available. Lithium-ion batteries and So lithium-ion batteries currently used in electrical vehicles or all other electronics applications because of the high energy density. Supercapacitors we generally called a next generation energy storage devices. I will explain what are the difference between these two devices and what are the advantage and disadvantage of the devices actually in future coming slides. So actually, thanks to this guy, actually the Nobel Prize is 2019 is rewarded by development of lithium-ion battery. The lithium-ion batteries is used for different sectors or from electronics to consumers. Without these three guys are really this very big achievement in chemistry sectors. Because good enough is now 98 years old. He is going to celebrate his birthday very soon. Then advanced energy material, advanced functional materials also conducting this the webinar and honor him for the special issues. So thanks to this guy, because this guy only developed the that lithium-ion batteries. So last year 2019, it's given the Nobel Prize in chemistry. So when you're talking about that device, so generally so many people are focusing on in India, particularly in abroad as well, by material development. But material is not the device. So we need to make the material and we need to assemble the device. Some we need to go for the technology. Then if you go for the technology only, the commercial utility and commercial application we can focus. So material development is very important. Then we need to convert into the device. These are another sectors to go for the technology transfer, the technology demonstration. So that is the main core area of ARCI. We are not only developing the material, we are also developing the device and convert into the technology to the Indian industry. So generally in India, if you see the institute and industry interactions is very less, because the government and universities are working alone, separately. And if you see the private sectors, for example, industry, they are working in separate sector, because there is no much collaboration between the government organization, universities, as well as the industry. You can see this is the technology readiness level. From this technology readiness level, we come to know that which technology is we are. So technology level 1, 2, 3. This is the basic research most of the government and universities are focusing on. Another hand, if you see the private sectors or industries, they are mainly focusing on that technology level higher than the 7, 8, 9 this level. But there is a huge gap between the academic sectors as well as the industry. So there is no collaborations. That is the reason, most of the people are developing the material in lab level. They are not converted into the prototype level, and they are not going to interact with the industry to develop the technology, to transfer the technology. So there's huge gap. Not only India, in abroad also is there, but India is more this gap. So we need to fulfill the gap to develop the indigenous low-cost technology. Then only this lab into that prototype devices. Then prototype devices is directly converted into the industrial sectors. Then only we can go for the commercial applications. So if you see I said the lithium-ion battery supercapacitor. So lithium-ion batteries is a very high energy density, but if you see the another hand, supercapacitor is low energy density, but it's having high power density. So these two devices are complementary devices. Lithium-ion having the high energy but low power, but supercapacitor is a low energy but high power. You can see the watt-hour per kilogram. Supercapacitor having 10 watt-hour per kilogram, but Tesla battery is having 232. Now the advanced battery having 300 watt-hour per kilogram, that generally using Tesla parts and all for lithium-ion batteries. You can see that the specific energy is given by lithium-ion batteries. Specific power is given by supercapacitor. If this is a well-known Aragon plot, the energy density and power density. So the conventional capacitors is falling on here is having very high power but low energy. But supercapacitor is in between batteries and capacitor, so it will fall on the in between categories. So it's having the high power but less energy. But nowadays people are integrating this lithium-ion batteries, the supercapacitor, in order to meet both power and energy. So this is a very simple example. For 100-meter race is generally we call supercapacitor, because supercapacitor having the very rapid flash delivery of the energy in fraction of seconds is called power. So that's the reason it is in the 100-meter race they need more power. Then it is the unit energy released in very short time is called power. So we can reach the destination very fast. The same thing marathon. If we see the marathon race, we need more energy. So the energy consumption unit time it's prolonged. So it's a long time. So that's the reason. This just for a comparison for the beginners or the students. This is the best example of comparison of supercapacitor and the battery. So generally, you see the large scale. Generally, as I said, this presentation is an energy storage device. But anyway, we are focusing now. I am focusing on the supercapacitor. But the ARCI, we are also working lithium-ion batteries to, as I said, material development, and we are making the device level, and we are testing the electrical vehicles application, other application as well. So here you see we are developing the in kg level material in, for example, LTO or on anode or cathode material. Then we are developing we have the very big line for the fabrication line for the batteries, and you can see we are finally fabricating the lithium ion batteries. But anyway, just I am not going in depth in this because I am going to focus on supercapacitor in the talk. So here, actually, any Indian scenario, if we see that, suppose we are developing the material, but we need the raw material. But you can see the raw material in India, there is no mines, lithium mines in India. So we are always getting the raw material from the outside of the country. So this is a problem for the developers as well as the industry. They need the raw material to develop the material. So in this case, it's a questionable, raw material is the questionable. So India should develop the own indigenous technology for the commercialization. So that's the reason now we are focusing on supercapacitor. So before going to supercapacitor, just I want to put why you need to go for supercapacitor. As I said, the supercapacitor having the less energy density compared than the lithium ion other batteries, but supercapacitor deliver the high power. That's the reason you see the lot of potential application is there. So before go to the supercapacitor, just now today I want to focus what are the applications is there, why we need to work on supercapacitor as an interesting field, and why need to develop the supercapacitor in India. So you can see the lot of potential is there, transportation sectors, and the renewable energy, and the industrial sectors, and the electronic sectors. Already you can see the 30,000 hybrid buses and 2 million startup vehicles are worldwide is implemented in ultracapacitor. Is almost 10 million ultracapacitor implemented in these applications. So it's a very huge market and for this one. But actually most capacitors are generally the Maxwell technology is the one of the world is a US company. You can see the Maxwell is concentrating on the low cells. For example, ultra small cells, 1 farad to 3,400 farads, and 2 modules. Modules is the combination of the supercapacitor in order to make the voltage. So it is a kilowatt. So modules we need to pack the single cells, for example, 2.7 or 3 volt. Then we need to for 48 volt we need to make the assembles. Then we can make the modules in order to get the kilowatt of energy. Then if you see the systems, for example, very big kilowatt or megawatt capacity, then we need to make all the modules to integrate into make the very big module. This is kind of grid application. We can supply the very big energy storage devices, or we can supply as well the grid applications, and the people are going for this kind of megawatt energy storage device. So not only this is anyway, I said Maxwell is developing from low end to higher end. Anyway, it depends on the capacity and the energy needed. There is a lot of sectors are having the power support, power, memory backup, and energy storage. For example, all the electronics and toys, all the electronic goods, generally supercapacitor useful for this, because supercapacitor energy density is less, cost is very high. For example, ultra fast camera and all, they need very fraction of seconds it will give the flash, so it need very high power. So in this case, very small supercapacitor can serve this application. So that is the interesting application. So for this lot of applications, the global supercapacitor market is really huge for the international level. We can see the consumer electronics is the already 22%. Then industrial, automotive sectors, industrial sectors, and energy sectors and others. You can see the distribution of the application in the supercapacitor. But particularly Indian market, now Indian market, consumer electronics is the top priority, and also people are looking for the consumer electronics. But energy sectors now slowly gain. We are also working in the energy sectors to implement the supercapacitor into the vehicles. So the expected growth is really huge. It's in the USD dollar is almost 2,000 millions by 2020. So the CAGR, the component annual growth rate, is already 16%, is really huge for Indian market. So in this scenario, as I said, Maxwell, there is a lot of companies, more than in world, more than 50 companies, supercapacitor manufacturers are there. But number one is the Maxwell, because Maxwell is the covering low end to higher end, all the applications Maxwell are doing, and it is almost 22-25 years old company. But if, for example, India, there is companies there. Yes, the Surya Powered Farad Engineering Limited is called SPEL, India first supercapacitor manufacturers. Anyway, you can see the list of top manufacturers in the world. It is very interesting to see that SPEL is also appear in one of the companies in the world manufacturer of supercapacitor. This SPEL is, we are also working very closely related to them. We are we already NDA signed and we are working with them. And that Dr. Rajendra Prasad is the CMD of this company. We are working on them. So this is very interesting. They already started the company, and they are producing the supercapacitor in Indian market. This is the supercapacitor. I said a lot of application. You can see the major application is the car battery. So supercapacitor can replace the car battery by 12-volt boost up pack, because it's when your engine start, then generally people are using the battery. But if you see this supercapacitor, then it will serve the purpose. But again, supercapacitor can charge by this again backup by the engine when you are called running. So it's regenerative braking. Also, there's another advantage of supercapacitor. When regenerative braking means whenever you are applying the brake, that kinetic energy convert to electric energy, it can immediately store the supercapacitor. So supercapacitor only can capture the energy in fraction of a second, very fast charge and discharge. That's the reason this supercapacitor can implemented in the core application. And also, you see the flight Airbus 380. The emergency door opening, people are already implemented. There is application is there. And elevator, as I said, suppose any power grid failure or any power supply, then it's a complementary device or the backup devices can be used in for the elevators applications. And also the forklift also people are generally implemented in supercapacitor, because it's a very fraction of seconds it charge, then it can release the energy whenever you want. We can because we need to take the one material to one place to other material, heavy material, so we need very heavy power and energy. So these kind of applications people are using for the forklift. And other medical applications, 1 farad to 10 farads also, there is the implement of the pacemaker, other medical aiders also people are using for this supercapacitor. So this, as I said, the flash applications, if it's already the smartphones and cameras, they already implemented supercapacitor. So if you see the without supercapacitor, even the night time, that photo is in block, is mean in dark. If you see the supercapacitor embedded system in night time, we can get the very the bright images. So because of the supercapacitor can really release the energy very fast, then capture the pictures. So that's already implemented in Sony Ericsson's. So another sector is transportation sector. Supercapacitor buses are implemented in China. Then you can see that implemented in here. This is the China bus. Already 150 buses are run by supercapacitor. So here the buses charged by you can see that the buses are charged by the grid line. Very fraction of seconds when the passenger get in and get out, the bus is charged and it go to the next stop. So you can see from the pentagram, the driver can note what is the state of the charge, very fraction of seconds. So within 10 to 15 seconds, actually, that supercapacitor can charge and it go for the next station. So it is around 10 to 15 kilometers. It can serve the purpose. This is already implemented in China, but this technology should come to India. That's why we are focusing on the electrical applications in our lab. I hope this video will. Can you see the video? Hello?
We can see the video.
Yeah, thank you. So you can see that from SOC, so means instead of charge, the bus is to go to the stops, then immediately charged, then it go to the next stop. You can see from that video. You can see immediately it is going to touch the grid. It's high voltage, because this supercapacitor is a very high voltage bank of supercapacitor put at the bottom of the bus. Then you can see that the driver can see the SOC state of the charge. Then it went to the next stop. Then this is another advantage. Supercapacitor is very fast charging, and also there is no life maintenance free, because it will go for 10 million cycles. So almost we can use for 10 years of this life cycle. That is the main advantage of this supercapacitor. I will show you why it's having such kind of a high life cycles. You see the latest advancement is the Lamborghini, the world first supercapacitor hybrid car is in it's a sports car. What purpose? Generally people previously using batteries, because battery only when start the car, because sports car always is driven very fast. When start the car, engine start up. So in this case, supercapacitor, if you put this, then you can start the car very fast, and it because of the power, it will pull the engine very faster. And also same time regenerative braking, because for sports car driver can apply a lot of brakes and a system, so it can regenerative braking also. It will supercapacitor very fastly charged by regenerative braking, then it will serve the purpose actually. That is the very advancements. Recently 2019 or 18 this was released, this car. And now I am going to this is just the overview of the extensively application of supercapacitor in the market, international market. Then what is the material point of view? What type of material we can use to why this material having such kind of long stability, long durability? You can see the supercapacitor is a next generation energy storage device. It's made up of carbon-based material. So porous carbon can use as electrodes, as a positive electrode, negative electrode. When applying the in between separate by the separator is electrically insulator and ionically conductive. And applying the electrolyte, put the electrolytes having ionization, so positive, negative ions. So just only simple mechanisms is when applying the potential, the positive, negative electron is the polarization. Because of polarization effect, it will separate and it form the electrical double layer. Because of the electrical double layer, it store the energy by porous carbon, then it will release. So it is charging and discharging mechanism. So in this case, there is no electrical, there is no chemical reaction. So it's a non-Faradic, no transfer of charges. That's the reason electrical double layer capacitor go for very long cycles. More than 1 million cycles is generally it will go. And but here, what is the problem? Cyclability is okay. Power also very high. But what is the problem? Energy density is very low, less compared than the batteries, and also compare than the other hybrid and other capacitors. For example, pseudocapacitors. In this case, pseudocapacitors, metal oxides is one of the anode or cathode we can positive electrode, negative electrode we can use. You can see the here in this case, pseudocapacitor charge transfer through the surface Faraday's reaction. So that's the reason the farads is very high farad. So energy density is very higher than the electrical double layer capacitor. But if you use a pseudocapacitor, life cycle because of the charge transfer, so life cycle is generally it is less compared than the electrical double layer capacitor. So that's the reason in the commercial application people are going for the electrical double layer capacitor because the carbon based, because it's very cheap. I will explain the next what are the material used. You can see the another type of the thing is, as I said, lithium ion batteries is high energy. If you see the supercapacitor, high power. So generally lithium ion batteries, as I said, the graphite and LMNO or other cathode anode lithium based materials are used for lithium ion batteries. If on the other hand, supercapacitor activated carbon only used, as I said. In this case, if you take one electrode from lithium ion batteries, one electrode from supercapacitor, it's called lithium ion capacitor. It's having the hybrid capacitor. So it has high specific energy and low high specific energy as well as high specific power. We can obtain this from these devices. You can see this is called generation 1, generation 2. For example, EDLC is as a next generation. But if you see the LIC modification, one electrode is from the graphite, another end from the carbon. It's called LIC. It's same thing. One electrode is a negative electrodes from the nanofiber is LTO, or because LTO is the metal oxide, lithium metal oxide material. But if this is electrically not conductive, so then that's why we put carbon nanofibers in order to make the electrically conductive the material. Then we make the put the electrode in the current collector. Then we make the negative electrode. This is the generation 2 type of capacitors. These two capacitors having the high energy density compared than the electrical double layer capacitor. You can see the energy density from here. The specific energy watt-hour per kilogram. For example, EDLC, the carbon based is less energy density compared than the other aqueous and non-aqueous hybrid devices. So depends on the application. Here actually material everything is because here cost, performance, durability, everything is interlinked, and for the commercial application. So the commercial people, industry people, they look on that whether it's cheap or high durability or it is having the less cost, like that. So depends on the application, depends on this industrial oriented, they will select. But generally EDLC is the now capacitor, supercapacitor is the marketable, is only based on EDLC chemistry. So this is a very simple phenomenon. As I said, the capacitance surface area versus the separation of the charge. So capacitance always calculated by farads per gram. So Q by V means how much charge accumulation by voltage. When increase the voltage, the charge is increased. So as per the equations, E equal to half CV square. So when we increase the voltage, then you can dramatically increase the energy density. That's why we are going for aqueous electrolyte. Generally we can go for 1 volt. Suppose if we go the non-aqueous, for example, tetraethyl ammonium tetraborate is the commercial electrolyte, that is go for we can 3 volt. Suppose then if you use that one, that is a commercial people are using, commercial Maxwell is using tetraethyl ammonium tetraborate only. So we can increase the voltage. So 3 squared will come. So energy density is higher. So the working principle is very simple. As a carbon based, this is you can see the YouTubes. The people are really simulating this work. Then if we are how the energy that ions are separated in the positive negative electrodes. The ions movements are well explained in YouTube. The interested candidate, they can go and see. So as I said, the price comparison, lot of material is developed. So we need to consider the performance as well as the price and the durability. As I said, for the commercial application, you can see that the year of the publication is indicate that a lot of people are working in this area to develop this kind of several materials. For example, carbon, metal oxide, composites, and all. But for the publication or the academic purpose, people are developing so many materials, and material design is very important for the, for example, commercialization. As I said, this is the main challenges and research activities toward the development of cheap and high energy density supercapacitors are very challenges. It's having the cost and performance durability is interlinked for the material for the commercialization. We can see that when I want to increase the voltage, I need to increase the organic. I can use the different type of electrolyte. Then we can use increase the voltage or asymmetric capacitors. It is I want to increase the capacitance means we need to increase the specific surface area, pore size, tunable parameter. We can achieve the high capacitance. So in this case, different type of materials already examined. For example, carbon, polymers, metal oxides, or ruthenium oxides, or in this case, carbon is abundant materials, very cheap. That's the reason Maxwell and others commercial supercapacitor using carbon-based chemistry. But now Maxwell also released metal oxide-based pseudocapacitor for the commercialization. So this is mostly all the development involved in this performance, durability, cost is the triangles for the industrial development. You can see the carbon, particularly carbon, as I said, carbon is the very abundant material, very cheap, but carbon is developed in different sources. For example, coal tar, coconut shell, nanostructured laboratory level, different type of methodology people are using to develop the nanostructured carbon. Graphene, graphene is the one of the familiar material for the different type of entity, polymers and polymer-based carbons and coke, petroleum coke. So in this case, we need to have some target for the industrial application. Now, presently, coconut shell is the dominant material for the industrial applications. If you see this, because you need to specific capacitance is 100 farads per gram, for example. The same time, the dollars, maybe $35 to $40 per kilogram is the commercial now present scenario. So if somebody is developed, this is a targetable. For example, 130 farads per gram in the same price, there is a winner for the commercialization. So in this case, surface area, as I said, the capacitance directly proportional surface area, but also there is optimization parameters there. If you increase the very high surface area, the gravimetric capacitance is down. Then you can see that the capacitance is down because of the very narrow pore size. Because if you very narrow, small pore size, the ions are not accessible by all the pore size. So that's the reason its capacitance down. This pore size is, I will show you the ionic. This is the thing one. You can see the pore size and that ionic size is very important. So which electrolyte you are using, there is a positive. For example, tetraethyl ammonium tetrahydroborate is a TEA, tetraethyl ammonium is a positive ions. BF4 is a negative ions. So how it's interact with the your porous material, then the pore size tuning is very important. You can see this, all the papers are really nicely discussed about the how the pore size distributions and how which material is suitable for the particular electrolyte and gives a very high performance and durability for the supercapacitor. That's very important. So in order to achieve this pore size, there is a people always going for chemical activation and physical activation of the carbon. But this is also involving the cost effect, performance, durability is very important. Which method is the best for the fine tuning of the pore size in cost effective manner. Chemical activation always problem, because if you use the chemical, then it's a environmental hazardous. Then after the chemicals, you need to wash the chemicals, to throw the chemicals. So that is the processing cost also including that. So that's a problem for the chemical activation. For physical activation, generally people are passing the air, steam, or CO2 as a physical activation agent. So this can create the pore size. But what is the problem is physical activation yield is less. The chemical activation is yield is more. But here both we need to consider cost. So physical activation, generally people going for the industry sectors, physical activation. Chemical activation, most of the academic people, they are using chemical activation because more yield and very easy to prepare. So as I said, the supercapacitor is very simple phenomena, carbon based chemistry, but really if you see the device level, it's a complex matrices, because there is a lot of parameters we need to control in the device level. Specific capacitance, then we have the resistance, operating voltage, then cell resistance, electrolyte resistance, and a maximum energy density, maximum power density depends on the final device weight. So This and all the lot of parameters for the we need to consider for the device level. But most of the people are considering in the cell level. That's people are telling okay, they're even the people are reporting even 1,000 farads per gram and all the cell level. But if you really that it got implemented in the real practical application, it's very far for the commercialization. So we need to consider all the factors in order to make the very good device for the commercialization. So that's why the indigenous material development is very important for the national development as well as the country development. You can see the various types of biomass used in the preparation of activated porous carbon. You can see the plenty of biomass, mostly particularly from China and other rest of the world. People are using almost all the biomass which can be converted to carbon. But can we use all the carbon can be commercialized? This is a question. No, because depend on the carbon yield, then impurities of the carbon. This is the matter for the commercialization. So here, generally, the coconut derived carbon is generally well known. That's the people are using coconut derived carbon. But what our group and we did, the selection of cotton, because the cotton is the world's second largest, India's world's second largest producer, and the waste, a lot of waste cotton we are throwing, and the industry also doing a lot of waste cotton. So that is the just we have that okay, why not we can use a cotton, because cotton is having the carbohydrates. When you burn the cotton, it completely it can convert to carbon fibers. So this economically feasible is there. So that's why I visited this the companies, and we collect the waste cottons and we are converting into the useful electrodes. At the same time, we are working on this eco green clean tech. It's activated carbon manufacturers in Tuticorin. Also, we are working on the activated carbon to convert it into useful products. Because coconut also, India is the third largest producer and is the fifth largest exporter of activated carbon. So we have plenty of resources in India, cotton as well as coconut shell. So that's the reason cotton we are directly converted into single step carbonization to the activation process. We are making the electrodes, and from the electrodes we make the very nice devices. And this paper is published in a Journal of Carbon, and you can see that the waste to the wealth. So we are converting the waste cotton into the energy storage device. So that's why we called waste to wealth or trash to treasure, converting this one. So from this, all the materials electrochemically well characterized in our laboratory. So we obtain, we are already coming, as I said, that voltage depends on your electrolytes. So 1 volt means all the aqueous electrolytes are for 1 volt, because if you go for 1.23 something is for example 1.23 is decomposition potential of water. So water can split into H2O2. That's why we need to stop at 1 volt for aqueous based electrolytes. So now neutral electrolytes you can go for 1.8 volt, and non-aqueous you can go 2.7. Now we achieve 3.2 volt also, depends on the electrolyte selection. You can go for, then we can increase the energy density. So then we did a lot of experiments on that, and these all are published in electrochemical acta and different papers. And as I said, this is cyclability. You can see that more than 1 million cycles is going. And not only we are doing this, then we made the laboratory cells. And as I said, 1 volt means we need to achieve like some of the devices we go for 5 volt or 6 volt. Then we need to always into combination, serial parallel combination of the devices to a demonstration of this kind of devices for the in order to see the proof of concept of the material as well as the device. And as I said, tetraethyl ammonium is organoid electrolyte. We can go for up to 3 volt. This rectangular is the typical EDLC behavior, because you can see the when specific capacitance versus cell voltage, it's having the perfect rectangular, means there is no resistance, and your capacitance is the behavior EDLC. That is a proof of that EDLC behavior. There is no peaks in the CV, so it means there is no redox reaction happening. The charge absorption desorption only perfectly happening. So it's a perfect EDLC behavior is we observe. And recently this article is very popular in India. We developed the waste cotton, and we also used the seawater as electrolyte. So low cost capacitor from industrial waste cotton and natural seawater can help energy storage. This is we published in Energy Technology. Then this is a very good comment from Dr. Harshvardhan, Union Minister of Science and Technology, as well as our Secretary Professor Astos Sharma. This study provides a solution for creating supercapacitor from abundant materials such as waste cotton and seawater. This showcases our country's vast potential and dedication to develop new source of renewable energy system energy. This is said by Dr. Harshvardhan, Union Minister of Science and Technology. It is an excellent example of the creative science for the sustainable green process, embedding principles of waste to wealth. This is said by Astos Sharma. So this is why I'm telling. Generally, people are thinking in we need to very simple process, then that can be easily to develop some end nice products. That's why recently we did a lot of work on this prototype level, and we demo different sectors of the applications with a different demonstration. And this is one of the very interesting application. Is generally this entrepreneur is coming from Pune. They developed the solar lantern by using the LS motor on supercapacitor, but this is the Korean company. They are using this their purchase from Korea, then they implemented in this Indian technology. This is very good product. From this inspiration, what we did actually, we purchased the commercial lantern and we test our supercapacitor devices. Then it's really giving very nice performance. Then this paper is also published in Global Challenges and all. So this another technology in Korean technology. You see the Maxwell capacitor. They are using the solar panel and they put the pole of the that the street light is the supercapacitor. So the both can survey the renewable energy and sustainable energy sectors, because generally photovoltaic can come for 10 to 15 years, and also for supercapacitor also it can come for 10 years. So it's having the, you can put this, then it's a maintenance free power supply, renewable, already demonstrated in Seoul, South Korea. Then we developed some other prototypes and we run the children's course, and you see this is the video review. Then we are really demo our own supercapacitor devices. We developed and this demonstration of this our own indigenous capacitor. So also we are developing the first supercapacitor driven bicycle in India. So proof of concept we already proved, then inaugurated by the ministers, science and technology ministers, and the DRDO, the chairman also there. And here you can see that the demonstration we did supercapacitor bicycle. There is a team involved on that. So we are working on the ARCI with the critical. We are developed this kind of technology. Okay, thank you. Thanks for actually I would like to acknowledge my students, because they did a lot of work in this all the projects, and the interested people, they can see our articles, all the will explain in these articles actually. So always I put the end of the slides. End is not the end. In fact, effort never dies. Success is depends on our effort. All the best. Be safe for these corona conditions. Everyone should wear the mask and be safe. Thank you very much for this listening the presentations, as well as for all the audience and organizers. Thank you.
Thanks for the nice presentation, sir. Sir, you can turn off the screen, sir.
Yeah. Yes, sir.
Sir, we have received some questions from the participants.
Yeah.
Let me ask one by one. The name is M. Aparna. She has asked, comparison of fuel cells and supercapacitors, which one is suitable for option for energy storage applications?
Fuel cells and supercapacitor?
Yes, sir. Comparing fuels and supercapacitor, which is the suitable option for energy storage applications?
Yeah, energy storage fuel cells better, because fuel cells having there is a huge energy storage, but because fuel cells can be stationary applications, it's not possible to put in this for the some mobility or depends on the applications. Supercapacitor is the always, because of the less energy density, is always a complementary device. You're not able to run the car only by supercapacitor, or you run the any commercial things. Supercapacitor can deliver very fast power. So we need to, wherever the fast power is required, there only we can apply the supercapacitor. Yeah. Hello.
The next question is, sir, can you hear me?
Yeah. Yes.
The next question is, what are the research opportunities available to the mechanical engineers in this field? What are the research opportunities available for mechanical engineers in this field?
Okay, that's a good question. Anyway, hey, I am a chemist and we are material scientists. Anyway, technology is not depends on one particular field of interest, right? Because, for example, if you develop the material scientists, of course, there is electrical engineers, mechanical engineers. If you want the production, chemical engineers. Then if you want the integrations, of course, mechanical engineers, for example, any application integrated sectors, of course, the mechanical engineer is required for the integrate the supercapacitor in the, for example, electric vehicles. So anyway, this opportunities is huge because now India is, as per the famous fast adaptation mobility plan, they are implementing electrical vehicles. So mechanical engineers, electrical engineers, there are huge opportunities for this line.
And one more question from Dr. M. Dakshinamurthy.
Yeah.
He has asked, what is the pore size? Which pore size is preferable for that would accommodate single TEA or multiple TEA?
Yeah, that's a good question. Actually, anyway, there are a lot of simulations activities people are doing for the pore size distribution of the carbon, but still there is not very clear, by frankly speaking, very clear evidence are not there. But lot of simulation activities, NMR studies are telling that there is a not single pore size because tetraethyl ammonium, for example, TEA is not a single ions. Always it's sometimes single ion, always it's having the solvation. So, for example, only TEA, that ionic size may be 0.6 nanometer or something. But if you have the solvation with the molecules, solvated effect, it go for 1.3 nanometer. So it's like we need to adjust what as per the commercial standard YP50, that is called Curare YP50, that is material only used in Maxwell. That pore size is having bimodal. Is most majority of the pores are around 1.3 and 1.8 nanometer something. So that is good for that particular electrolyte. So if you see the other electrode, you need to accordingly, pore size engineering is very important for the supercapacitor. You need to tune according to the ionic size and the solvation size. People are working on that. This is what we observe. This is the pore size 1.3 to 1.8 suitable for this organic electrolyte.
Thank you, sir. And another question is the same Dr. M. Dakshinamurthy has asked, do you use CNT as electrode? Is so as a coating or rod itself? Do you use CNT as an electrode or coating or rod itself?
CNT is good, but what is the problem? CNT is very long tubes and it depends on the quality also, because CNT always having some impurities. If good quality of the CNT is good, but what is the problem? Surface area very less for the CNT. So supercapacitor application, surface area also one of the important factor to more ion storage. So CNT is not good material for the supercapacitor. It may use maybe the composite. For example, some of the CNT is very good electrically conductive. So if it act as a bridging material, additive material for the some of the carbons, but generally coconut based carbon not required because already is electrically conductive. That is enough for the supercapacitor purpose. Yeah, hello.
What are the other uses? Can you hear me, sir? What
Yeah.
are the other uses of a supercapacitor and what are the drawbacks of supercapacitor?
Sorry, what are please?
What are other uses of supercapacitor?
Other uses, I already showed a lot of applications, right? In the beginning, there is a lot of application in supercapacitor. What is the drawback is supercapacitor is having the drawback energy density. So people are working to how to enhance. That's why I told some of the slides, hybrid system, we can increase energy density. Particularly supercapacitor main drawback is self-discharge because of the ionic adsorption desorption phenomena. If you want to charge the supercapacitor, within depends on the device prototype, the self-discharge is the problem. But anyway, you can charge again fraction of seconds. That's the advantage. But main disadvantage is the energy density.
Thank you, sir. That's all the question for today.
Yeah.
Now let me ask Dr. N. Sivakumar to do vote of thanks.
Yeah.
Sivakumar, sir, please come online.
Respected Honorable Dr. Karthik, Senior Scientist, International Advanced Research by Powder Metallurgy and New Materials, DST Hyderabad. most respected principal, respected HOD, and my dear colleague, and all the participants. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of PG and Research Department of Chemistry, extended a very hearty vote of thanks to Dr. Karthik, who blessed us with his presence and took out valuable time of his very busy schedule in research, though the nation is in a pandemic situation. I must mention our deep sense of appreciation for Dr. Karthik for his work and valuable time. I especially admired with Dr. Karthik's speech given us an inside out of advanced carbon materials for energy storage, which is a need of our in the 21st century. The way he explained the topic is exemplary. I also wish to express my gratitude to our principal, Dr. Deepa, for providing encouragement and support. I am very grateful to Dr. G. Rajagopal, head, for giving us opportunity to organize this event. Also, I would like to extend a special thanks to Dr. P. Vijayan for inspiring us with the webinar jam and Dr. S. Karthikeyan for his endless effort. I heartily congratulate all the participants for their active participation in this event. Yes, no program becomes successful with a single person. I extend my big thanks. Once again, I'm repeating, I'm expressing my big thanks to our department friends for their support. Thank you guys for making this event successful with your contribution. Thank you one and all. Thank you.
Thank you for the welcome address, sir. That's all for now. So we are going to end this session. Thank you very much. Thanks for one and all.
Thank you.